In this video I am going to review how light travelling through a semicircular glass block into air changes its behaviour depending on the angle of incidence. The reason I'm using a semicircular block is so we can focus just on what's happening at the glass-air boundary. That's the boundary here. You're looking at this bit of the experiment. By shining the red light onto the curved surface, I'm avoiding refraction at the first air-glass boundary. Here, the light is at 90 degrees to the curved surface. Let me show you. 90 degrees to the surface of the curved edge of the block. So, the light is coming in from a source over here. It's coming in through the air into the glass, and we're not interested in that boundary. We're interested in the light that's travelling through the glass here and then meeting this boundary with the air here, the glass-air boundary. This is where we're interested in. So the light is coming in along the normal line. Both sides of the red ray of light hit the new material, the glass, together. The light slows down, but it doesn't change direction. So I want you to look at the top boundary, the glass to air only. Here, the angle of incidence can be measured between the ray of red light and the normal line here. Here, the angle of incidence, I, is 10 degrees. And the light is being refracted. Instead of coming out here, it's bent away from the normal line. As the light hits the air from the glass, it speeds up. And because one side reaches the air before the other, it changes direction by bending away from the normal. Here, the angle of refraction, R, is this angle here, which is measuring at 15 degrees. Now I can use these results to calculate the refractive index of the glass. I can use Snell's law to calculate the refractive index. Snell's law says that the sine of the angle of incidence, sin I, divided by the sine of R, the angle of refraction, is equal to nR over ni, where n is the refractive index of the two materials at the boundary. So here, nR, the material that refracted the light in our experiment, is air, and ni, the material that the incident light was moving through, for us, is the glass. So for our results of an angle of incidence of 10 and an angle of refraction of 15, sine of 10 degrees divided by sine of 15 degrees is equal to 1 over ni, because the refractive index of air is 1. So I have calculated on my calculator 0.174 divided by 0.259 when I've worked out the sines of these two angles, and I've rounded those. So that's equal to 1 over ni. 0.67 was what I found on the calculator to be equal to 1 over ni, and then rearranging the equation, ni can be found by doing 1 divided by the 0.67. So the refractive index of the glass came out at 1.49. So each material has its own refractive index, and air has a refractive index of 1. Now I know the refractive index of this glass, I can use it to work out the new angle of refraction or a new angle of incidence. Say I set the angle of incidence at 20 degrees, I could work out where it should come out at. So sine of 20 divided by the sine of R will be equal to 1 divided by 1.49. I've calculated the sine of 20 to be 0.342 on the calculator, so divide that by sine R and it will give me the 0.67. Sine R can then be rearranged and calculated by dividing the 0.342 by the 0.67, giving us 0.51, and when I press inverse sine on my calculator, I find the angle of refraction should be at 30.7 degrees. So, the angle of incidence set at 20 degrees and the angle of refraction measuring round here at our calculated 30.7 degrees. Say instead I want the angle of refraction to be at 48 degrees. I could work out where I need to shine the light in. Sin I divided by the sine of 48 will be equal to my 1 divided by 1.49. So the sine of I divided by 0.743 is equal to the 0.67 that we've seen before. Sin I can then be rearranged so that I times together the 0.67 and the 0.743, giving me a value of 0.5. And when you inverse sine 0.5, you find the angle of incidence needs to come in at 30 degrees. So with the angle of refraction set here at 48 degrees, we can see the angle of incidence coming in at 30 degrees. Okay, so if I is equal to 0, if the angle of incidence is straight down the normal line, the light goes straight through the material. Both sides of the light are reaching the boundary at the same time. So, although the light changes speed, it doesn't change direction. If the angle of incidence increases from that 0, we start seeing refraction. So, as the angle of incidence increases, the light comes in at an angle to the normal, and one side of the light leaves the glass before the other, causing the change in speed and direction. As the light speeds up, it bends away from the normal. It's refracted at the angle of refraction. And Snell's law lets us calculate things. I, the angle of incidence, R, the angle of refraction, Ni, the refractive index of the material the incident light was moving through, or Nr, the refractive index of the material that's refracting the light. As long as we know 2 bits and we remember that air's refractive index is 1, Snell's law will help us out. But remember, if the boundaries are the other way round, Nr and Ni are the other way round too. I think it's time to find out what happens if we make that angle of incidence even bigger. If we keep increasing the angle of incidence, the light behaves differently. At bigger angles, like 50 degrees here, we see total internal reflection. All the light is reflected inside the glass. We can also see this at 60 degrees and at 70 degrees. At bigger angles of incidence, like 50, 60 and 70 degrees, we are seeing total internal reflection. All of the light is reflected inside the glass. Now the angle of incidence and the angle of reflection are always the same. The law of reflection is applying now, so when I is 70 degrees, R is 70 degrees, where I is the angle of incidence and R the angle of reflection. So, small angles of incidence, we're seeing refraction and we're using Snell's law. And larger angles of incidence, we see total internal reflection, and the law of reflection is what we're going to use. You know what we've still got to talk about. Yes, there is an exact point, an exact angle where behaviour changes from refraction to total internal reflection. This angle is different for different materials, and it's called the critical angle. When the light comes in at the critical angle, when the angle of incidence is equal to the critical angle, or I equals C, it causes refraction to be at 90 degrees. At the critical angle, the angle of refraction is 90 degrees, always. So, Snell's law is handy again. We can use it to work out the critical angle for any material. For our experiment, going back to Snell's law, sin I over sin R is nR over Ni. But now I is C, the critical angle. So sin C divided by the angle of refraction is now 90 degrees. So the sine of 90 is equal to our 1 divided by 1.49 because we're still working with that same glass to air boundary. So sine c divided by 1 is equal to 1 over 1.49 because the sine of 90 comes to a nice handy 1. The sine of c then is 0.67, and if we inverse sine 0.67 we find c should be at 42 degrees. So let's check. We're approaching 40, we're getting to 42. Now the light is refracted at 90 degrees, and now past that point we're seeing total internal reflection. We've seen the behaviour of light travelling from glass to air changes as the angle of incidence changes. When I equals 0, it goes straight through. When I is less than c, the light is refracted, obeying Snell's law. When I equals c, the light is refracted at 90 degrees, still obeying Snell's law. And when I is greater than c, the light is totally internally reflected and obeys the law of reflection, I equals r. And that's it. Keep up the revision, because you know that
regular review gets a better grade for you.
Don't forget to
Like,
so that I can keep making the videos.
comment,
Especially to request other revision topics.
subscribe.
So you can get notifications of when my next video gets uploaded.